Now that we've defined functions and discussed how they are related to relations, we can talk a little bit more about them in the context of an equation. Now, when we defined a function, we sort of intuitively thought of it as a rule that assigns an input to exactly one output. So an input to exactly one output. And we can think of this as from some element of the domain to some element of the range. And we also, if we kind of think again back to algebra here, when we thought of domain and range in algebra, we thought of those as the set of x values and the set of y values. And so we can kind of utilize that again here, where we're going to really be able to think of functions as assigning some x input, so some x value input to some y value output. Okay, and so when we write an equation, even something like y is equal to 3x plus 1, we have this sort of built in, right? We can plug a number into x, evaluate the expression on the right-hand side of that equation, the 3x plus 1, and then get a value for y, right? So we could do something like, if x was 1, y would equal to 3 times 1 plus 1. We plug in that input of x, and we evaluate this expression. 3, of course, times 1 is 3, plus 1 is equal to 4. And then we get a y value output as y is equal to 4. So we input the x is equal to 1, we output the y is equal to 4, and so we can sort of think of this equation as a function, right? And even more specifically, that 1 that we plug in only has exactly one output. It can only go to 4. There's no other like algebraic magic that can happen in between that's going to come up with some alternative value. So we've got 1 in, we get 4 out. Now, beyond just writing these as x and y, because we want to be a little bit more precise with the symbols that we use to represent this stuff, we actually have a function-specific notation. And so let's look at a function notation. This sounds really fancy, but really all that we're saying when we say a function notation is the way that we're going to denote a function so that it's really clear what the input is and what the output is and what is the expression that defines that rule. So the way this works essentially is we're just going to write something like f of x equal to, and then we're going to put our expression here in terms of x. So equal to an expression in terms of x. So when we write it out this way, what we're really saying is that this x value is equal to the input. So we're plugging in to this function whatever value we put here. We call that x. And this f is the name of the function. And you might be saying, well, that's kind of weird, right? Why would we even bother calling it f to begin with, right? Why even come up with a specific name? Well, there's actually lots of functions that we'll see a little bit later on that utilize this sort of notation and have actual names to them, right? So for instance, we'll see something like log of x or sine of x, or other expressions of this nature, other functions of this nature, I should say, where we actually write out the name of the function log or the name of the function sine and put the x, the input, in parentheses. So what does this actually look like in practice? How do we actually utilize a notation like this, where we have f, the name, and then an input like x surrounded in parentheses equal to some expression that determines how we're going to evaluate that function? Well, let's actually try to do some evaluation here. We've got two examples here. F of x equal to 4x minus 3. Right, in this case, again, we've got an input of x, so x is our input. We've got a function named f, and here we have the expression that determines how we're going to evaluate this, determines the rule that's going to take that input, process it, and give us the output. And likewise, we have the same on the right here with g, right? This is a different name, we call it g, but it still follows the same format. And so our task here is going to be to evaluate this for x is equal to -2. So that's our input in this case. We're going to take -2, we're going to input it into the function named f, and we're going to also input it into the function named g, and see what the corresponding outputs are in both those cases. So let's start with f. We can write this like this now, because we're not just talking about some arbitrary or unknown value x, we're actually talking about what this specific output is going to be when we input -2. So we can go ahead and write -2 inside the parentheses. We would say this like f of -2. That's going to be kind of how we pronounce this out loud, right? So this would be read, I'll say read f of -2. And then we can write the expression where we plug in, or we substitute the x, right, which was up here. Every time we see that x, we substitute it with the input, with the -2 in this case. And so our expression was 4x minus 2. So instead, we're going to substitute the x with this was 4x minus 3. And so instead of writing x, because -2 is our input, we're going to substitute that x with -2. Now notice that I'm putting parentheses here, and that's going to be pretty important in a lot of cases. Maybe in this specific instance it doesn't make a huge difference, but in a lot of cases, like the one that we're going to see coming up soon, this is a really big deal. So I'm just going to highlight this here. Make sure to include parentheses, because that's really going to help us keep track of keeping those inputs together, right? We use parentheses in algebra to keep quantities together. Our input is its own quantity, so we want to make sure we surround that with parentheses. Now from here, yes, we've got this nice expression, but of course we have all of these algebraic and arithmetic tools that are going to allow us to evaluate this and actually get some specific value output, right? So we'll use our order of operations to say, well, we've got to multiply this 4 times this -2, and that's going to give us -8. And then we've got to subtract this -3 from this -8, which is going to give us -11. And so this here would be our final answer, but also the output of the function f when we input -2, right? So we can say, kind of as a summary here, and I'll draw these 3 dots. That sort of just means in summary or in conclusion. F of -2, so our function value at an input of -2 is going to be an output of -11. And so we can sort of write that like this. Now, we can do exactly the same thing we just did, but for our function g as well, right? If we want to take g of -2, all we're going to do is find every instance of that input in the expression, so every instance of x, and replace it with -2. So here we have -2 squared plus 3 times -2 plus 1, right? And again, here it's going to be important that we use those parentheses, right? Because that's going to change the way that our expression would play out based on the order of operations if we didn't. But since we have them, now we know that we're keeping that -2 together, and when we square this, it's going to be -2 squared. So we have minus from here times the -2 squared, which is going to give us a positive 4, plus 3 times -2, which is going to give us -6, plus 1. And now you might be saying, well, that says -4. Yep, that's true because this negative sign is dropping down. This becomes +4, this negative sign drops down, and so that gives us a negative times a positive, or -4. And so from here we can then just do the subtraction. -6 minus 4 is going to be -10, and then +1, -10 plus 1 gives us -9. And so what we can do is we can say, therefore, g of -2 is equal to -9. And this would be our final answer. So when we input -2 into g, the function g outputs -9. Now, that thing that we input into the function, it doesn't just have to be whole number values like -2, or even just values at all. It could be a whole host of different things, including its own expression. We could even at some point, and we'll see this a little bit later, plug in a function as an input to another function, like function inception.
What's happening?
Cobb's drawing Fisher's attention to the strangeness of the dream.
But for now, we'll just look at an expression. So let's take a look at this example here, and we'll see if we can evaluate f of x plus 3, so this expression here, as our input, into the function f of x equal to 1/2 x plus 3/2. So this might look like it's a lot more complicated, but in actuality, it's going to do exactly the same thing that we just did. We're going to take this input of x plus 3 and find every instance of x in our equation and just replace it. So we've got f of x plus 3 now has to equal 1/2 times x plus 3, the quantity. And again, we're using our parentheses here, right? We want to remember the parentheses. And then we have plus 3/2. Right, and if you kind of think about this more broadly, this really makes sense, right? If f of x is equal to 1/2 x plus 3/2, then f of x plus 3 should equal 1/2 x plus 3 plus 3/2. And so this really does work nicely. From here, we can simplify our expression using the same tools of algebra like we did previously. Now, since we still have a variable, we won't get this down to a set value, but it will give us a expression that will count as our output here. And so we can distribute, for example, and so we have 1/2 x plus 1/2 times 3, or 3/2, and then plus 3/2. And then we can simplify even further by combining like terms and adding 3/2 and 3/2 to give us 1/2 x plus 6/2, or 6 divided by 2, which is equal to 3. And so we have 1/2 x plus 3. And this would represent our final answer. So we could summarize as, therefore, f of x plus 3, right, the quantity x plus 3 is equal to 1/2 x plus 3. And so now we can use function notation and we can evaluate functions at certain inputs. But if we were given a generic algebraic equation, are they always functions? Now, in order to answer this question, we have to remember back to the specific definition of a function again, which is a rule that assigns an input, a rule that assigns inputs to exactly one output, to exactly one output. Or as we can kind of often think about it in the context of an equation, is that each x is sent to exactly one y, exactly one value of y. And so if our equation satisfies that, then it would be a function, but if it doesn't, then it wouldn't be. And there are actually some examples of this, and there are some that you might already be familiar with already. Now, to figure this out, essentially what we're gonna wanna do is we're gonna wanna get an explicit expression for y, for the output, right? So if you've noticed, right, if we notice, everything we've done so far so far we've written y is equal to 3x plus 1, right? We've written f of x is equal to 4x minus 3, and so on and so forth, where the output is isolated all by itself on one side of the equation, and then the expression that determines the output, that rule that does the assigning, is all by itself on the other side. And when that's the case, it's going to be really easy for us to determine, is there one output or could there potentially be more? And so in order to determine this, if we're given some arbitrary equation, our first step most of the time is just going to be, can we get y or f of x or whatever the output of our equation is? Can we get that isolated all by itself on one side of the equation and then look at the rule on the other side that defines it, right? And so our goal here, what we'll need to do is we'll need to solve the equation for the output, if it's not already in that form, for the output. So it's defined explicitly. Defined explicitly. And when I say explicitly, I just mean here's y all by itself, here's precisely the rule that determines the output on the other side. In contrast with something like, say, if we had x plus 2 squared plus y minus 4 squared equal to 9, right? Something like this is the equation of a circle, and this is an implicit equation because yes, we can figure out y, but we have to do a bunch of work to get there, and it doesn't just tell us automatically based on a single expression like this over here, right? These equations we would call explicit equations, explicit. And so our goal is to solve for y, get it isolated, and then we're going to be able to determine whether or not our function is an equation. And so let's look at two examples here. On the left-hand side, we've got x squared plus y equal to 9, right? This is not defined explicitly because we don't have y, the output, all by itself. And then we've got x squared plus y squared equal to 9 on the right. Again, y is not by itself, so these are implicit equations. If we take that first step in determining this and we solve for the output, we solve for the output, right? In this case, that's just going to be y. Then we can start to do some algebra here to isolate y. Let's start with part A. If we want to get y by itself, we can subtract x squared from both sides, and that's going to give us y is equal to 9 minus x squared. On the other hand, or on the other side for part B, if we want to get y by itself over here, we would first have to subtract x squared, similarly giving us 9 minus x squared on the right, but we also have this y squared on the left. And so we'll have to take the square root of that in order to get y by itself. Now, what you'll have to remember here is that when we take the square root of a value, that has both a positive version and a negative version, right? So we would have to consider both the positive square root of 9 minus x squared and the negative version of square root of 9 minus x squared, right? And this is just because if you think about kind of an easy example here, if we had 2 squared, that would give us 4. If we had negative 2 squared, that would also give us 4. And so the square root of 4 could be either the positive 2 or it could be the negative 2. And so we've got to remember both the positive and negative 2 in this case here when we take that square root. But what that shows us is that in this case here, there are two options. There are two options for y for a given x, right? It could be the positive version or it could be the negative version. And so since there are two options there, and we know we can only assign one output in order for this to be a function, we would say, therefore, this is not a function. And on the left-hand side here with part A, 9 minus x squared does not have anything like that, right? If you plug in some number for x, there's only one thing that's going to come out. And so we can say, therefore, this is a function, is a function. And so that's really going to be one of the main things you'll want to look for when doing this. If you are solving for y and you get some kind of plus or minus square root, that's going to usually be a good cue that, that you're not going to have a function. All right, so hopefully you found that helpful. We'll see in the next video if we can expand these concepts to also talk about graphs. So we can take all of the stuff we've learned now about relations and equations and functions and start to visualize it on a coordinate plane and kind of see how these rules all play out there. But in the meantime, I hope you enjoyed this video. Of course, let me know if there's anything I can do to help or if you have any questions. And I'll see you in the next one. Have a good rest of your day.